Good afternoon, everyone. Uh, we will be presenting our experience about autonomy deployments with the Autoware Stack. So, I am Tanmay from Clemson University's International Center for Automotive Research, where I am pursuing a PhD directly after my bachelor's in mechatronics engineering. And the focus of my research is digital twins, more specifically the real to sim transfer, where I'm looking at things like modeling, estimation, and simulation of real world entities. And me and my twin brother Chinmay will be presenting today. He also is working in the field of digital twins, no pun intended, where he is looking at the other side of the coin, which is sim to real transferability. And with that small introduction of ourselves, let's see what we have on our presentation. So first we'll be talking about how we encountered Autoware, which started with the Open Connected and Automated Vehicle, or the OpenCAV, at ARMLab. We'll quickly brief about AutoDRIVE and Autoware integration. We already discussed this in the earlier talk, so we won't delve into that. Then we will talk about the new Autoware-enabled platforms that we are using and developing in ARMLab. And finally, we have something really exciting to unveil today. So kind of excited about that. So let's first talk about how we got started with Autoware. This is a vehicle that not just got us started with Autoware, but also our PhD. This is called the OpenCAV, or Open Connected and Automated Vehicle at CU-ICAR. It's basically a Chrysler Pacifica hybrid retrofitted with drive-by-wire and a whole host of sensors for localization, perception, object detection, and tracking. And all of these are now automotive grade, so you have a full-scale vehicle on the campus, which is also connected via a dedicated cradle point to the 5G network. And so you can, of course, do V2X communication with this. One of the things that got us really excited about the software stack, which is Autoware, is its ease and nice and clean integration with the low-level drive-by-wire interface. And so we could quickly set up a demo of mapping an environment, generating a trajectory, and then tracking it autonomously to provide campus rides that are autonomous to any visitors that come to our campus, or even just for our research as well. So we'll now just quickly brief over the AutoDRIVE-Autoware integration. For those who didn't get a chance to attend our talk earlier, AutoDRIVE is something that we have been developing for a few years now. It's an open source digital twinning ecosystem which offers a test bed and a simulator, which are digital and physical representations of each other. You've got different vehicles across different scales and operational design domains. The first and the third column here represent the physical vehicles, whereas the second and fourth ones represent their respective digital twins. Similarly, you've also got the different environments to operate these vehicles in, ranging again from small scale to full scale and across different operational design domains. On the other side of the screen, you have different interfaces to observe and interact with these digital twins with humans in the loop. And finally, and most importantly, you have different sets of APIs and frameworks that now support development of autonomous driving software stacks, as well as smart city software stacks, and cleanly interface with the simulator with a zero-shot capability of transferring your algorithms from simulation to reality. So here is what we have been able to do with AutoDRIVE and Autoware integration. We have been not just able to set up demos, but we have also open sourced all of these for the benefit of the community to get started with Autoware. So here, for example, you see the F110 Thor RoboRacer vehicle, which targets the autonomous racing domain in simulation, interfaced with the Autoware stack. And here now you have the same vehicle running in the real world with the exact same algorithm without any retuning of the parameters for perception or control. So basically, it's a zero-shot transfer, and that has been the norm with AutoDrive to simplify the sim-to-real transition. Here you have a different operational design domain and a different vehicle. So here we have what we call NIGEL, and we'll be talking a little bit about NIGEL in the future slide as well. But this is now targeting autonomous parking, ODD, and same as earlier, you have a zero-shot sim-to-real transition for autonomous parking using NIGEL as well. And here I'd like to just highlight that the Autoware stack is running on board these small scale vehicles. We had to optimize the stack so that it could be both compiled and run at the edge devices such as Jetson family of devices. But yeah, that's something that has been released open source as well. And finally, here you have the OpenCAV shuttle service demonstration in simulation first, where we are taking a route from point A to point B. And then you have a similar transfer in the real world, where we, as I said, can provide shuttle rides from any point in the campus to any other point in the campus because we have mapped the campus already. So for example, here on the left hand side, you have a ride that's going from AVX lab to the Carol A. Campbell Graduate Engineering Center. And on the right side, you have the exact opposite ride, which is going from CGEC to back to the AVX lab. And Chinmay here is basically taking his hands out of the window to show that he's not driving the vehicle. But what's more important is with the digital twins, we can now immerse the physical and digital worlds sequentially or in a step-by-step manner, where, for example, here we wanted to test an emergency braking algorithm where it becomes safety critical for direct physical deployment. And that's where we now leverage the digital twin ecosystem to hierarchically stage the deployment from pure simulation, where we just had the AutoDRIVE Simulator interfaced with the Autoware Stack, to emulation, where now certain aspects of the perception as well as dynamics were emulated from real world data, and all the way up to stimulation, where the full framework that you see on the right kicks in action, where you have a physical vehicle that's driven on chassis dyno. Its physical sensors are stimulated via different stimuli, such as the projector screen that stimulates camera, radar target stimulator that stimulates the automotive radar on the vehicle, as well as different equipment to stimulate the steering forces or even the GNSS and other sensors of the vehicle. This then feeds back into the digital thread to update the states of the digital twin of the vehicle within the virtual environment. And then now back the virtual environment is streamed as the ego view from the ego viewpoint to make sure that the physical cameras on the vehicle or physical sensors on the vehicle actually receive those stimuli from the virtual world. And in this way, we can now safely deploy any algorithms on the physical vehicles, but with the luxury of testing indoors and safely. So for example, here you have the Autoware stack running the AEB demo. Everything's running on the OpenCAV that's being visualized here. This feed is, and the data that's coming from the chassis dyno rollers as well as the steering force emulator and other sensors of the vehicle goes back into the control room where we have the simulations running. And the simulations then take up this data, update the states of the digital twin, and then that's how the ego viewpoint is updated and rendered. So that was something that we have been working on and that got us into Autoware. But going forward, we are now excited to extend Autoware deployments to new platforms. So the first platform that we are working with in-house is development of an autonomous electric go-kart. And this is a design that we have partly inspired from the Autoware Foundation AV for EV go-kart, but we have significantly redesigned some of the systems to make it automotive grade reliable, so that this idea of expanding the automotive grade reliability into the field of robotics to make the autonomous vehicles in general safer and reliable is something that we wish to pursue with this kind of a platform that's custom built. So, to be honest, we are not just talking about the design here. We have already started to build this in the real world. And here you can see the different tests that we have conducted. Some of them are a bit old and some of them are pretty recent tests that we conducted. So the very first stage, which is the video on the right, you can see that we are testing the electric go-kart in a completely manual driving mode. But on the left is what we accomplished more recently, is we are now able to have a vehicle state supervisor that can now enable us to perform the by-wire actuation of the steer by-wire, throttle by-wire, as well as the brake by-wire systems on the go-kart pretty reliably, with the functionalities for handling different faults, as well as making sure that the systems are performing reliably and safely. So with these tests now underway, we are slowly but steadily towards the completion of the build portion of this. And what's next is just interfacing this with the endless possibility of autonomous driving algorithms that we can implement, test, and further optimize in terms of both the software and or the hardware aspects of the go-kart. Now let's address the elephant in the room, which is PIXKIT. So we had the opportunity of working with this platform for some time now, and as you can see, we have explored the different capabilities, including the front wheel steer, four wheel steer, and the wedge wheel steer of the platform. But wait a minute, that reminds us of something. We had taken up this research project called NIGEL. So NIGEL was the first vehicle that we designed from ground up, and it was the first native vehicle of AutoDRIVE ecosystem. And the key idea was to promote the mechatronics engineering approach of hardware software co-design and foster the concurrent engineering principles and the interdisciplinary system design approaches into autonomous vehicle design. And so we came up with this vehicle prototype, which is 1/16 scale vehicle for in-lab research or experimentation. And as you can see from the picture on the slide, we just bombarded it with a lot of functionalities and components for perception, planning, as well as control tasks. But what is unique about this vehicle architecture is that it has an independent four-wheel drive and four-wheel steer capability, which enables us to actuate each and every wheel in terms of both its steering as well as velocity. And that can help us achieve some of these interesting maneuvers much in the same way as PIXKIT, for example, the wedge steer that you can see here. But now, instead of just stopping at smaller steering angles or Ackermann constraints, since we have a fully controllable and redundant system, we can leverage the benefit of extended steering capabilities of 90-degree crab walking, for example, as you can see currently in the video. Or we can also form skid steer configurations with minimal slip. So in the current steering configuration, you don't have the slipping or the skidding of the wheels, but you can still turn on the spot. And so all of this has been open sourced, including all the designs of hardware as well as the software of this prototype vehicle. And we have also created and curated the documentation in terms of the build manual, as well as a bunch of video tutorials have been released on YouTube that can basically help the community get started with planning and control strategies with respect to such interesting vehicle configurations. And what we are aiming to do now is to extend all the research that we have been able to do with this small scale vehicle to the full scale or partly full scale PIXKIT that we have in the lab, so that we can work on interesting approaches for motion planning strategies and especially the control system design for such unique architecture of the vehicle. One of the interesting things that we also observed as a part of our research, which is cited on the slide number 2, is that when we try to develop robust control algorithms for such systems, we encountered that the four-wheel drive or four-wheel steering capability of the system gave it a superior measure of performance, and that's how we know that the design is in fact much superior to conventional Ackermann steered vehicles, for example. And so that opens up a huge avenue for potential research in this direction. So coming back to PIXKIT now, what we were able to achieve is build a vector map out of the tiny town environment in AutoDRIVE Simulator. And that is what you see depicted on the slide. It has multiple features such as parallel and perpendicular parking lots, as well as controlled and uncontrolled intersections, both four-way and three-way. So we typically use this scenario as a benchmark environment for testing on-road autonomous driving applications. And what we were able to do is spawn the PIXKIT in simulation over here. And then using the Autoware free space planning, which uses the hybrid A* search algorithm, we were able to plan paths from the spawn point to the designated parking lot. And this is where the PIXKIT is in simulation performing the parallel parking maneuver. So as you can see, the PIXKIT backs in first and then parks in the designated parking pose that has been given to it. So this was one of the early stage explorations for the planning and controls applications with the PIXKIT. But we have also tested out perception based algorithms. So here what we are doing is object detection and tracking, wherein you can see the person walking in front of the vehicle is detected and tracked as a specific object. And we can also see these detections across the different objects that are available in the lab. The most interesting part is when the vehicle reaches the other end of the lab, where we have a few parked vehicles. And that is when the object tracking really becomes crucial, because all of these different detected vehicles are assigned a specific identification number, and that number stays constant despite the vehicle motion or any relative motion between the vehicle and the other objects in the scene. And with that, we now have something exciting that we would like to unveil to the community. So without further ado, we have the PIXKIT digital twin in AutoDRIVE Simulator. It is modeled based on the exact PIXKIT that we have in ARMLab, specifically PIXKIT 2.0 that we have in our lab. We have tried to model the vehicle dynamics aspects as well as sensor physics aspects as close to the physical parameters of the real vehicle as possible. For example, the same videos of the real vehicle that you saw earlier, the digital twin can also perform Ackermann steering for the front wheels like a normal car. It can do four-wheel steering, which reduces the turning radius significantly and creates tighter turns. And you can also do wedge wheel steering, which basically allows you to crab walk across the lanes without changing orientation. We also have added interfaces to lights and indicators of the PIXKIT, which are directly supported by Autoware. So signaling and driving at low lit areas is also something that you can test in simulation. And you can also use the indications to the device multi-agent planning or V2V communication indirectly, using the indicators as a means of communicating your intentions. And finally, here you have the entire digital twin of PIXKIT 2 in action, where we are trying to visualize the different simulation streams to give a glimpse of what all is possible. And of course, with AutoDRIVE, Autoware, and PIXKIT coming together, the possibility of devising your autonomous driving algorithms is endless. So we hope that this contribution helps the community. And with that, we conclude our presentation. Thank you for your time.